All right. Hey, everybody. Welcome. We're in week 12. Um, just looking at where we are here, it's unclear to me if I'm going to finish today, but I guess that's a bit the beauty of a video lecture. Like, if I give a 15-minute lecture next week, you don't have to commute for it. Okay. We'll see how it goes. So I guess I was sort of wrapping up big data stuff here and coming to really the tail of the course. And got to this point where I was saying like, okay, like, well, what if you need big data tools? Like for this semester, we have this compute cluster and it's there and it's running and you can just log in and use it for free, right? That's great. Well, I guess this might be the case in the company, right? Like you might get a job and they say, oh, there's your cluster and off you go, run Spark stuff or whatever. If not, well, hopefully somebody has a budget for you. And the thing with our compute cluster is, one, we kind of need it to be there for y'all. Like if you want to work at 4 in the morning, fine by me. Maybe make better life choices, but it's not my problem. Usually this is not the case, right? Usually in big data tools, you have like lumps of analytic work to do, and then you kind of don't need that compute power for a while. So you probably want to not pay for it all the time, right? Like buying hardware and installing it, that upfront cost usually isn't the thing. So there's things like Databricks is the Spark company. Like Spark came from a lab at Berkeley. Those people founded Databricks. Like Spark is Databricks and Databricks is Spark in a very real way. They have an AI sales assistant. Sure. It is what it is. You pay for their cloud offering. It is very deeply integrated with the Spark ecosystem. There are things added to Spark specifically for that kind of deployment. It's great. It fits. Amazon Elastic MapReduce is Amazon's version. And I mean, they called it Elastic MapReduce when the MapReduce framework was a way to do big data stuff. It's also perfectly good Elastic Spark. The deal here is you basically say like, okay, I want a compute cluster. Like I want Spark stuff. I want this many compute nodes and I'm going to pay for them by the hour or whatever, and bring it up and then destroy it when you're done, or put it to sleep or whatever the verbs are here. Or just, computers, wherever you can get compute power, you can do this. But do you need a cluster? And like this, of course the answer is it depends, right? As I've said many times, the answer to every good question is it depends. Good questions don't have like simple answers. But like you can go to Amazon and you can just get 192 cores and 1.5 terabytes of RAM, and then just like effectively infinite data storage coming from the object store. So you can just get one of these. Like you could just like bring up an R8G 48XL with like Ubuntu or whatever, pip install Spark, read data from S3, and off you go. Spark is good at using many CPU cores. Like you've seen it happen on your computer. Maybe not a lot, but maybe like when you've run a Spark job, you've heard your fans on your laptop spin up in a way that you're not accustomed to. And that's because it's using all your CPU cores. Okay, if you had a lot, then why not? Sure, go for it. So I think Spark is a great tool. And I know Spark runs on a cluster. That doesn't mean you have to have a cluster to run Spark. Think about this. Like this is such an easier setup. Bring it up, take it down. I don't know what the pricing is on that. Hopefully if you need it, right? It's not your personal problem. $11 an hour. I mean, on the grand scheme of things, that's you get that's a lot of computer. Anyway, 11, I don't know what currency units, I guess. Okay, so I wonder what big data is in the modern world, I guess, is my point on this slide, right? Like, I don't know what my phone is if I wave it around, but like, well, I don't know, like 10 years ago or maybe more, but like this feels like a lot of computer and it fits in my pocket. So, I mean, think about how much data, like what's the biggest data set you've ever worked with in a like serious way, right? Like outside of a class or whatever. Um, would it have fit on this pocket computer? And if so, well, do you really need big data tools for it? Um, I think the answer is both no and maybe. Like, you don't need, for most data sets that most of us use or most on your project or whatever, you don't need big data tools. That doesn't mean you're not allowed to use big data tools. And this is certainly the conclusion I've come to over the years, that Spark ain't bad. Spark, like working with a data frame in Spark and working with a data frame in Pandas or some other tools we'll talk about, isn't really so different. It's, you know, you have to spell things different. Spark takes a little longer to start up, but once that's taken care of, it's fine. You know, put this column here and join on that column and whatever, and you can spell that in Spark. And then you have this sort of expandability or something. Use all your CPU cores, whether it's 4 cores on your laptop or 192 cores on some massive Amazon VM or whatever, and great. And then if I do need, you know, we come to the point of like, this isn't going, guys. We need more compute power. Let's set up a compute cluster. You're kind of ready for it. You know, if you've written your code in Pandas and you come to that point, you're rewriting a whole bunch of stuff or using some compatibility layer, and that's just uglier. So I kind of like I like Spark this way, and sometimes I do, like I have code that manipulates data to like create data sets for this course or whatever. I often find myself just writing it in Spark because I don't worry about memory and stuff that way, and I know it'll expand if I need to, and just why not? I can write Spark. The compatibility layer I mentioned is the Pandas on Spark API. And this is basically, the problem here is I have Pandas code, I'm out of memory, I need Spark, I don't want to rewrite my code. And the idea is basically they have re-implemented the sorts of things you can specify in Pandas and like have a like conversion layer of that into Spark. So like the thing that's happening here, right, like right away is this PS is the PySpark Pandas compatibility layer. And so instead of pd.read parquet, I'm ps.read parquet. And now it's a Spark data frame, but not quite, because it's a Spark data frame that I can work on using Pandas code. Like the code that I had that worked in Pandas, we hope, continues to work in this context, except with Spark backing it up. So, okay, that's great. Like Spark scales to bigger data sets. It runs on a cluster. And this is the real promise that they're making is, yeah, but you know, all that Pandas code you have, it'll work. Usually. Yeah, like, okay, some features aren't there. Some features don't make sense, right? There's things you can express in Pandas that just do not make sense to do on a distributed data frame, like a Spark data frame. So well, maybe you don't get to do those, but maybe that's okay because you didn't do those, right? Okay, like, does it matter if we change our code to lazy evaluation? Well, of course, it depends on your code. So this is an option. The things that I've made you do in Spark on the weekly exercises, where I'm sort of forcing you to slam your head into the limitations of Spark or the weird things that happen in Spark, like I don't have enough partitions, or I have too many partitions, I have imbalanced partitions, joining is expensive unless it's a broadcast join, like all of those things. Of course, there's no way to spell those thoughts in Pandas, right? Pandas doesn't have a repartition or a broadcast join hint or whatever, because it doesn't need them. But if you're going to start doing it on top of Spark, maybe you need to express those thoughts. Again, maybe not. There's a lot of perfectly good pandas code out there that, oh, you know, our data used to be a gigabyte, and now it's 100 gigabytes, and it will run just fine in this way, and we can just not have to rewrite our entire pipeline. We just have to rewrite the like first lines and the last lines to read the data differently or whatever. So I think this exists. You probably should know it exists. I guess you should never, here's my advice. You should never plan on using the Pandas Spark API. It's there if you need it, but you should try to not need it. So, like I said, I will, you know, if I think the data might be big, I'll just start writing in Spark. It's fine. I know it takes a few seconds to start up any Spark job. Okay, and I think I've said this before, like it means if I have a Pandas job that takes 4 seconds and I don't like that it takes that long, well, Spark is not going to fix my problem. If I have a Pandas job that takes 20 minutes and I don't like that, well, then this 5-second startup doesn't matter, right? So in my head, there's this category called medium data that's like, well, I don't need a compute cluster, but I also don't want to keep the entire thing in memory in arrays and work on it single threaded like Pandas does. And in that medium ground, maybe Spark is still a winner. Or, and I think I mentioned this before too, I've definitely heard people talk about Spark in like a strictly ETL context, and some of you will be doing that on the project as well. Because you might be starting with a big data set. You downloaded some massive data set, or it's on the compute cluster, or it's kind of awkward and weird, or you know, you have every single event that ever happened, and what you really want is each individual's average, and then you have a much smaller data set or whatever. So maybe this is the point of like, well, you can start with Spark. You can say, step 1 of my data pipeline is an ETL task where I extract the data from the big data set. I transform it by turning it into a much saner, easier data set. And then I don't have big data anymore. So that might be something like this. And like, I've done this kind of thing before. In fact, again, like all the data, like if I'm giving you data sets this semester, like the weather data, the Reddit data, all these things are extracted from genuinely large data sets. They've gone through some process like this, right? That's filtered in some way. If you're going to use it in Pandas, it needs to be turned into a single file. And I guess I'd better be confident that that's okay in this scenario, whatever I'm doing. And then if I say coalesce 1, I will be creating a directory with a single file. Okay, and now I think, okay, I have small data. I can move back to Pandas, and I can use scikit-learn and the stats tools and whatever else. And then I can read my one file, right? As new line delimited JSON, which is what I saved as back here. And great. Now I'm in a non-big data context with my data. Great, I've done ETL. I've moved on to step 2. Also perfectly good, very realistic use of Spark. So I feel like, just as a good member of the SFU community, I mean, some of you, of course, are in this program. This perfectly good SFU major in data science, I believe is the right term here. Which I don't know, it exists. It's wow, we're really not describing the program here. It's effectively a joint program between computing, stats, and business. Compared to other data science programs in the world, it's a little heavy on the business requirements, and I'm not sure that's bad. You know, what are you doing this for if not, you know, in some context where the answers matter? And obviously business is not the only one, but maybe. So I don't know, like it's probably too late, but if you're in like computing and you're just not vibing with it, maybe this is a thing worth looking at. If you're in it, cool, love it. Another option, we have this master's, Master of Science in Big Data. Again, we keep I keep getting told like, no, you're using the wrong term. Okay, it is a Master of Science in Big Data. It is part of the Professional Masters in Computing Science programs. I think this is correct. I've been teaching the first lab in this course forever. It is, again, it's a professional program. It's designed to be, pretty time boxed and pretty practical, I guess. If you want to talk, I think if you want to talk about the big data masters, I don't know, probably just find me in the lab. If this stuff we've been talking about for the last couple of weeks, again, if this is something you're into, have a look, maybe. Anyway, so where are we at here? We're just there. Okay, so we enter the end game of the course very much here. I guess communicating, very much a core data science topic. These next couple slide decks are some like tool systemsy things that I want to talk about because I love it and I think it will make you a better person. This first one, like I had a bunch of cautions on exercise like 3-4 that were like it's not the lesson I intended. Let's put it that way. When I first gave this question, I had students coming up to me and saying like, oh, my program takes 60 seconds. Is that okay? And I thought, what? Like mine takes, I don't know, I press enter and it's done. Why does yours take 60 seconds? And I think there's a story here that's worth telling. They're all doing the same job, right? These students were getting the right answers. And so I'm going to simplify and this kind of thing. Of course, the N is pretty arbitrary, but chosen so I get decent times. And okay, I'm doing that calculation. Obviously, this is simpler than the Haversine calculation, but it fits on a slide. So I claim that the problem here is a leaky abstraction, where, of course, pandas and Spark and friends, they give you this fiction that there's something called a data frame. And they give you methods to work on it. But like some of those methods are easy because they map onto like whatever's going on inside the computer naturally. And some of them are slower because they don't. And it's that abstraction of, oh, you have something with rows and columns. But of course you don't have something with rows and columns. You have something made of bytes in the computer's memory. And if ever there was something I believe, it's that abstractions leak. And I have said this, wait, how am I confusing this course in 295? I said this in 295. Okay. What Pandas does, when Pandas store stuff in memory, each series is stored together and the data, I mean, there's some metadata, but the actual data, a million rows, each series column is then a NumPy array of a million things, which means this is cheap, right? If I want to talk about the column, this is just like a reference, right, to a thing that's already hanging out in memory. This, where I get row 0, it doesn't look anymore, there's like the same amount of punctuation on either line or whatever. This doesn't look expensive, but it is, because that row object doesn't exist in memory. It can be constructed, but it has to be constructed. So anytime I can talk about a pandas series, probably that's the right thing to do. And this is part of the reason that there's been like no loops all semester, because it forces you to take, okay, this series times that series or whatever. Or yes, more concisely, pandas is column oriented. So this kind of thing where I have type annotated here, which I haven't usually been doing this semester, but just to be clear what's going on here, that I have a function that takes an argument, but now that argument is a whole array, or it could be a pandas series, like both close enough for me. And then I'm going to do this on arrays, right? So I'm going to subtract 1 from everything. I'm going to take the sign of all of those. I'm going to add 1 to all of those and return it. Obviously, there's a loop in here, right? Like somebody is responsible for subtracting 1 from all of those, but it's not me. As we like, again, as my brain is in Compute 295 mode as well this semester, part of the reason this is fast is A is, again, effectively an array in memory. And I have all of these SIMD or vector or SSE or whatever you call them instructions. So this -1 isn't done one at a time in a for loop. It's done big blocks of however many things fit, and I'm striding 4 or 8 elements down at a time and using these instructions that are great, and I paid for them, and I've got the transistors for them, so I want to use them. So this is the baseline, 3/4 of a second. Let's make a note. 0.75 seconds. So the other thing that you could do here is if you sort of, in this function, you forget that NumPy and pandas exist, and you just write a function that takes a single number instead of an array. Well, Python can work on single numbers. So math.sign instead of numpy.sign. And one of the things that I think legitimately confuses people is np.sign, if you hand it a number, will give you back a number. Like, it will work exactly like this function. So you could use np.sign in this context and fool yourself into thinking you're doing something that's not really going on. But the way I've done this is for everything in the column, call this Python function. And I pay for that, right? I pay for that with a I don't know, what is that? 15 times speed difference. Because there's a little bit of cost to calling a function in Python. There's a little bit of cost to doing a conversion. What's in this is just a straight up C-style, or an array of just C-style floats. They have to be turned into a Python float object, I guess, sorry, C-style double. They have to be converted to a Python object, this, and then convert back, times a million, right? Because you're doing this once for every element. Okay, like, in some ways it's miraculous that it's only that much of a slowdown. Or a very similar result for the NumPy equivalent, right? So this is the exact same function, except instead of a pandas series.apply, I'm doing an np.vectorize to make it look like I've got a function that works on an entire series, but doesn't really. It's just a for loop that somebody else wrote. And, you know, similar, like this one's a little faster, but pretty similar performance overall. In exercise 3/4, you had to do this once. Like, you had to apply, okay, which was it? So it's every city, every weather station. So you had to do a, like, for every city, call the function, but then inside that, you should do the work in a NumPy way. So it's one city and all weather stations inside your calculation. If you didn't know that, or if you had a thing that did work on a single element at a time, what you had to end up doing was this twice. And then instead of calling this with a column or a number, you're giving it a row object. And remember, this row object doesn't exist, or this collection of row objects doesn't exist. So they all have to be constructed, and then passed over here, and this thing does its work, and then you really pay for that. So again, we're 0.75 seconds up to 194 seconds. Massive speed penalty for this. And even though it kind of looks the same, right? Do this to each thing. Do this to each thing. Like, I might, if I was only going to get a few words, I might describe them the same way, and they're very much not the same. If I had let you from the start of the course write loops, and you took the perspective of like, well, okay, I don't want to learn new things. I'm just going to keep doing the things that I wanted to do, or that I already know how to do. Or I'm a C programmer who is determined to not actually write Python code. I'm just going to write C code. I'm just going to spell it with Python syntax. Either way, you would end up with this kind of thing, and you're penalized for it. And the difference here is, like, it's a Python loop, I guess, compared to either the vectorize or the apply. This is a, like, implicitly some kind of like C-based loop that the nice NumPy people have optimized as best they can. This is a Python loop that, you know, you get what you get, and you pay for it. So 3/4 of a second up to that. Huge speed penalty for these things. But it turns out you can do a little better. Just because of what NumPy is. I guess we talked about lazy evaluation in the context of Spark, and I'm pretty sure I said that Pandas isn't, or NumPy. So when I say a-1 here, that is evaluated right now. It's not an execution plan in Pandas or NumPy. It is a calculation that is resolved to an array. So calculate this, put it in some temporary spot. And then for each one of those, calculate the sign of them, put it in some temporary spot, and then add 1 to each one of those and throw away the intermediate things. That seems like it should cost a little bit, and it does cost a little bit. Well, okay, that link's not very informative. The numexpr package, I assume it's pronounced, is sort of one way at least to recognize this within a NumPy context and fix it. And so what happens here is you give it this expression that gets compiled, I think these are the words I want. And then like I'm sure your syntax highlighter is going to complain here, right? That you don't use the variable a in this function, but it does get passed in, and this a in this string turns into a reference to this a from the local variables. And then numexpr is free to sort of say, okay, what I should do is for each thing, subtract 1, take the sign, add 1, and put the result here. I don't need those intermediate arrays. It should be a little bit faster, right? And this doesn't come up that often. I think I tried it on exercise 4. It didn't make that huge of a difference, but it can matter. In this case, it actually mattered way more than I thought. You can ask for it in a pandas context this way as well, if you don't want to have the library hanging around. And I looked at this for a while, and I thought, that seems faster than it should be. And I actually tried writing it in C, and my C code was noticeably slower than that. My C code should be able to, optimize my C code and everything. But I ended up here. So, I'm like 3 orders of magnitude difference on this chart, right? Like this is a massive speed difference for the same calculation, right? Like it's all of these are order n. It's just that the constant on that n is massively different. So I kind of have to have this in mind, right? If I can do things the right way, I should, right? This is easier. Like I think I would argue easier than these other things for exercise 4, including the Python loop. All of those would be harder. There would be more code. This is easier once you know how to work with pandas and NumPy. And then I would think of this one as like, oh wait, I can bail myself out if things do go wrong, or if things do start to get slow, and I don't want to switch to Spark or something like that. So like I said, C took a little bit less time than that, and that's totally what I would expect, right? There's a little bit of extra like overhead to doing Python NumPy stuff, but then the real work ends up being done, as a C-based implementation that has been compiled and optimized and everything's great. So I expect my C code to be faster than that, and that was my hypothesis, and it bared out. But then I had this number, right? That is many times faster than my C code, and I didn't know why. And I actually had to really dig. Like it took a while for me to explain this, because in numexpr, the documentation for this is buried, that it actually multi-threads your calculation just magically, just for free, for no extra work. It's like, oh, how about I start some threads up for you? And I break your array up into 64 chunks, and I'll start my 64 threads and use all your CPU cores. And it did. So that's awesome, right? Like if this, again, frequently asked or frequently uttered sentences in my life is, you bought those CPU cores, use them. And this is one way. And this is how much work I want to do. None, right? I didn't do anything about concurrency. I didn't have there's no mutex or whatever, or if there is, I didn't write it. It just, goes real fast because some nice people wrote this numexpr thing and decided to use all my CPU cores. In the same way that like the nice Spark people did some stuff and use all my CPU cores. Great. I want that to happen. I don't want to worry about mutexes. And with the right tool, you get that. So yeah, I think this is the lesson that, and it's why I like teaching a course like Compute 295, which is, if you're not into computing, what's the course title? Computer Systems or something? Introduction to Computer Systems. Because there's no such, at some point, like there's no such thing as a data frame or, a series or whatever. There's just some bytes in memory and some instructions that your computer can run. And okay, you get presented with this high-level object that has many fun methods that you can use to get stuff done really easily. You just need a couple neurons firing off, keeping track of, well, what's really going on here? Is it okay? Is it okay? And most of the time, those neurons don't have to assert themselves. But boy, sometimes you can really save yourself. I think one of the lessons here, right? Like, again, C code optimized as best I could. Like I tried to write normal but good C code. Well, I didn't have to, right? Like I think that matters, right? Like I got a relatively modest speed penalty, but I got to write fun, beautiful Python, and it looks easy, and it's easy to debug, and it's easy to get right. And I didn't have to worry about malloking memory or whatever. Great, I like that. And it's what I want from NumPy and Pandas and friends. So yeah, if you'd like to try it, that Jupyter Notebook, it's going to be obviously different, like different hardware, different versions of the libraries. These numbers have been reasonably stable as I've rerun this demo over the years, but yeah. Let's talk about some other ways to do this fast. And this is in the context of, I like data frames. We've had 2 data frames tools over the semester, and they're a nice way to think about my data, right? Rows and columns, and do this operation to all of those kinds of things I can express, and that's great. There are others, and Pandas is by far the most commonly used data frame tool. Like I mean, citation needed, but I don't think that's a contentious statement. But is it the best data frame tool? I think that very clearly no. Except, of course, the reason that we're using it, because everybody else uses it. So if you have a problem with Pandas, Google and Stack Overflow and ChatGPT or whatever are all going to know how to deal with that in whatever combination. Spark, I haven't tried for a version or 2, but like the LLM certainly used to hallucinate insanely with Spark because there's just not a lot of Spark code out there to train on. So they would often, I think, it'd be like, oh, I have the concept of data frame and I know how to do that. And they just like switch to some Pandas code somewhere in there that obviously wouldn't work. So let's look at some other, even less common sort of data frames tools. So I'm going to reproduce something you've done in the exercises. So you did it with Spark as, again, like I think a realistic-ish, something you could imagine for your project, right? This, it was the same week as the quiz, so you weren't paying attention. But anyway, hey, I've got this format. It's what I got. It's what got downloaded. And I want only this data because that's the question I'm going to answer next in my project. And, only these rows, only these columns, and in this format because it's what I want. Or that could have been Parquet or something else, right? Totally realistic, I think, ETL task. And then I have added a little bit to it just because I wanted to. The dates are in this weird format that are almost a date. Like this is December 31st, 2013. but it looks like an integer. Like it looks like the integer 20 million and whatever. And then I just decided, like the problem is, what's the hottest temperature each day within Canada? Just because. Okay. If I wanted to do this so again, you did this, well, the first half of this in Spark. I've continued on a little bit. So pandas is everywhere all the time. Again, it's the thing that people know and people discuss and talk about and answer questions about. And it's a sort of baseline for like all of these other tools I'm going to talk about that can do data frame stuff. Like if you can't convert a pandas data frame to and from your data frame library, everybody's going to look at you like you're stupid because, yeah, I've already got this thing that produces a pandas data frame, or I want to use your, I want to do steps 1, 2, 3, and 4 in your shiny new tool, but yeah, step 5, I need to do it in pandas because I already have the code or whatever. So all these conversions are there. But in the context of like we've just been talking about big data stuff, pandas is, I think this is fair to say, the opposite of what I want in a big data tool. Everything is materialized all the time. And that's, well, I guess that's usually what I expect. Like most of the time when I program, right, when I say variable name equals, I expect the variable will hold, in memory that. And that's what I get with pandas, normal programming. Strict evaluation, yep, not lazy evaluation. And if I have a lot of data, now I have a cost, because if I store, I have 12 steps to my calculation and I store 12 integers in memory, yeah, no problem. If I store 12 data frames in memory, well, how big is that data frame? And leaving a few tools aside and NumExpert, when I say, again, add 1 to this series, I'm only going to use 1 CPU core to get there. I paid for a bunch of CPU cores. I kind of want to use them. But again, if I have 100 rows of data, all of this is cool, right? If I have a small data set, I don't care about that. It's totally reasonable. But let's move on. I had to not, like I'm starting with, So in the exercise, you had a directory of many CSV files. Pandas doesn't do that. So I had to, like, outside of my pandas code, concatenate all those together, ungzip them, and have one input file. And this is pretty much, I mean, it's obviously spelled differently than when you did it in Spark, but there's no header row. So I had to say there's no header row, and also please name the columns these useful names. And also, like I said, this looks like an integer, right? Anything that would automatically detect data types, which pandas is doing here, would look at that and say, oh, look, digits, no decimal point, integer. So I had to say, no, please keep it as a string. And then do the thing. Throw away the bad quality, keep only Canada, keep only the Tmax. And then the next, oh no, I guess this, keep only the columns I care about. This is where exercise 9 ends. And then I decided I wanted to do this date conversion. Dealing with dates always, like the conversion of dates always sucks. This seems to be the way. Oh, sorry, that's also in exercise 9. And of course, every time I do this, by the way, like every data frame is in memory, and this is not an insignificant amount of memory. Okay, so I did this copy to silence the warning about copy on write sort of situations. Maybe I used extra memory by doing that. Now that I say that, I didn't think about it. I did this because it shut up a warning. Maybe I used a lot more memory because I did. Well, I felt like I was a good pandas programmer when I wrote it, so I'm going to go with it. But I did try, like I didn't create a new column value. I replaced value and I replaced date. So I hope I'm not using extra memory for all of these. And I did rename this to that in place. So I didn't make a new column and then delete the old one. I just renamed it in place. That's an option I've got. And then I guess continuing down my new task, I said I wanted the max temperature on each date. So I have this like juggling around of things to get the right column names and whatever. And output is JSON. Okay. I redid this morning. So what I had done was I had always done this on the weather 3 data set that you had for exercise 9. And the times that we're getting were just not, they were like my data set was too small basically for these tools. So I got a bigger one. It's about 3 times as big as weather 3. It took about a minute. It used a not insignificant amount of memory to get there. I mean, the original CSV file is around about 4 gigabytes. And I mean, I guess that's probably somehow related to its size in memory, but not identical. But okay, I have a copy of the data set there. I have another copy of at least some of the data set there. I have another copy of some of the data set there that I try to manipulate in place, and then another copy. But this is pretty small data by now because group by date, well, 1 row for each day. This is now small data, and I don't care about it. Or I don't care about it, at least as far as memory footprint goes, but this is not nothing, right? Like yeah, I have 32 gigs of memory on this desktop. On my laptop, I would have been in trouble with 16. So we have big data tools. I mean, if this is big data, I'm using too much memory in a small data tool, I'll use a big data tool. So I did the same thing in Spark. But yeah, I know this, right? You know this from working with it the last few weeks. Spark starts to feel heavy, is the only way I can say it. Like you get all those warnings and like 3, 4, 5 seconds just to get started. There's a JVM hanging out there. It's pretty fast. It's 2026. I don't know why. Just like if you just think about the JVM, it takes a gigabyte of memory. Anyway, and maybe I don't need a big data tool here, right? Like I have all of this like complexity because I want to be able to scale to petabytes of data. I don't have petabytes of data. I have 3 point whatever gigabytes of data. So the big data tool can do this, but maybe it's overpowered, I guess is my like comparison here. So what was it, 62 seconds before and 23, okay, wait, 62, 23, okay, so it took 1/10 the time, way faster. Used all my CPU cores, my fans probably spun up for those 6 seconds. It used a very modest amount of memory, and this is one where, again, like switching from weather 3 to weather 4, I had 3 times as much data. It used the same amount of memory because all of the things where the data is actually big in this calculation are still pipeline operations. So I can just do them, aggregate by day, and then it has to start doing shuffle things. So very small amount of memory, again, didn't really increase with the size of the data set, and went really fast. That's great, right? Because it's lazy evaluated, I'm not storing, well, I guess what I'm storing as intermediate results is an execution plan, not the data. So, okay, that's great. That was a total win, right? 1/10 and 1/10, like 10 times or better on both axes. That's great. But what else is there? So polars, polars is as far as I'm concerned, the up and comer here. Oh, they've changed their tagline from what I have quoted on this slide. So yeah, okay. Again, for like open source as the banner, right? It's not, they're not, I guess what I'm saying here is there's a lot of projects that I would refer to as begrudgingly open source. Like they like the part of open source where people use their tool and get locked into their tool and write code for it, but they don't like that part where people use it for free. Polars is sort of seems openly open source, right? Like they do want an open source tool. So it's implemented in Rust, which is kind of neither here nor there, but at the same time, when people say implemented in Rust, they mean I care about every byte of memory and every CPU cycle very, very often. But I can call it from Python. So I'm gonna. So it's import polars as PL, so I'm using that. Polars can deal with the multiple files in a directory style. Otherwise, I have, I have the same thoughts as what I said in pandas. These column names, and don't look for a header row, but please keep that as a string. I had to say all the same things as pandas, but I can now do this. I hope, if it's going to multi-thread, I hope that it can read all my files in separate threads. Maybe that'd be cool. And then again, I would refer to this as just the same ideas but different spelling. The column Q flag. So on the data frame, look for a column Q flag, and I want it to be null, and look for a column station, and it starts with CA, and look for a column this. So different, same thoughts, different spelling. And I can do a bunch of these things as separate operations, as combined operations, right? I can do the divide by 10 and the date conversion and the throw away the other columns all as one select operation. That's nice. It's nice compact code, and I like it. A group by and the max temperature and sort and write it. Great. It turns out, and I almost said lazy evaluated, and I almost lied. That code that I just showed you is strictly evaluated, actively evaluated, whatever you call it. Filtered weather is a thing that exists in memory, which I then use to do this, and then I never use again. So, okay, maybe I used extra memory by doing that. Maybe I want, I like lazy evaluation is not without its pain, but maybe I like it. Maybe I'm willing to accept that. Again, you saw some of this stuff in the exercises for Spark, but I like the idea of the optimizer. I like that, Spark will, if I never use a column like the S flag or whatever, it never reads it. It just passes by it and doesn't bring it into memory, and that's great. I want that to happen. And it turns out I can ask for it in pandas. So what I showed you a few slides ago was read CSV. If I just, literally this is the only change it to scan CSV, it gives me back, instead of a data frame, a lazy frame, which is just what it sounds like. It's a data frame, but lazy evaluated. And then at the last step where I had done that, just take this data and write it, I can say .collect, that turns it in, it turns a lazy frame into a data frame, and then I can write that to disk. So I get the full query optimizer in that story, and I don't store all my intermediate results, and I win as a result. So again, pandas was here. So just using data frames in polars is very fast. Using the lazy evaluated data frames in polars is super fast. I'm now more than 10 times. Oh, that should be gigabytes. Well, let's take a break. I'll fix that, and we'll pick up from here.